Hi guys, I'm Abhinav. This is our team.
Hi guys, I am Latik Abhinay.
Hi guys, I am Harshil Solanki.
Hi guys, I'm Shashank.
Hi guys, I'm Mohana.
Hello guys, I'm Tejasri. In this video, we will showcase you the journey of making our drone under the project in MS101. We started working on our drone from 8th March. Our drone is made of determination and seamless hard work, crossing various checkpoints on its way into the sky. A drone is a small flying device controlled by someone on the ground. It can be used for various purposes like shooting aerial videos, surveillance, delivering packages, and even helping in search and rescue missions. Our drone's chassis is constructed from lightweight yet robust carbon fiber, ensuring optimal performance both in terms of weight and strength.
The name quadcopter itself suggests that our drone contains four propellers. It contains two clockwise and anti-clockwise rotating rotors placed diagonally in order to cancel out the effective torque. The four propellers give us four control surfaces, namely throttle, roll, pitch, and yaw.
Throttle governs altitude by adjusting vertical moment. A higher throttle raises the drone and a lower throttle lowers it. Roll tilts the drone left or right along its longitudinal axis, enabling lateral movement akin to steering. Pitch tilts the drone forward or backward along its lateral axis, facilitating forward or backward movement. Yaw rotates the drone left or right around its vertical axis, allowing changes in direction without altering its position in space.
The throttle of the drone can be controlled by increasing or decreasing the RPM of propellers, effectively going up and down respectively. The roll of the drone can be controlled by increasing or decreasing the RPM of one side of motors relative to the other side, effectively moving the drone left and right respectively. The pitch of the drone can be controlled by increasing or decreasing the RPM of front motors relative to the rear side and effectively moving the drone forward and backward. And finally, the yaw can be controlled by increasing or decreasing the RPM of the motors in one diagonal relative to the other diagonal, effectively rotating the drone clockwise or counterclockwise.
The Arduino Nano microcontroller serves as the central processing unit for our drone. We will upload sketches to this microcontroller to program its behavior. The code will then execute to control the drone's functions. The Node MCU is a 32-bit ARM microcontroller. It features built-in Wi-Fi capabilities for wireless communication. This allows for signal transmission without the need for physical connections. For tilt sensing, we employ the MPU 6050 sensor board, which features three accelerometers aligned with the X, Y, and Z axes. These accelerometers feed their output into three analog-to-digital converters (ADCs), each with a 16-bit resolution, converting the data to digital values. These values are stored in six 8-bit registers accessible to the Arduino via a serial interface.
We are using a ESC Simon K30A, an electronic speed controller, which is a device that regulates the speed of an electric motor by varying the voltage and current supplied to it. We are using a LiPo 3S Orange 1800 mAh battery pack featuring a lithium polymer composition consisting of three cells connected in series. It boasts a capacity of 1800 milliampere hours.
The TS helped us while soldering was done. This sheet was the plan for soldering. The battery provides power regulated by the buck converter to power distribution board, which in turn distributes power to all the components of the circuit. The Node MCU boots up and connects the Remote XY app on the phone to receive input from the joysticks. This input is translated to Arduino using channels. The Arduino also interacts with MPU 6050 to understand the current configuration of the drone. It then processes these inputs and makes the current required adjustment using PID algorithm. It provides output to ESC, which controls the power delivered to the motors and the direction of rotation, which is explained in the section of dynamics of drone.
The drone controls are run on the Remote XY application, which is a graphical user interface. This is how the Remote XY controller screen looks. The left joystick controls the throttle and yaw, while the right joystick controls the roll and the pitch of the drone. To decrease the throttle, we move the left joystick down, and to increase the throttle, we move the joystick up. To make the drone take a left turn, we move the left joystick to the left, and similarly, we move the joystick right to make the drone take a right turn. To move the nose of the drone up, we pull the right joystick down, and for the nose down, we pull the joystick up. And finally, to roll the drone towards left, we pull the right joystick to the left, and similarly, we pull the joystick right to make the drone roll towards the right. After setting up the circuit, we ran codes through the drone in 4 steps to calibrate the MPU. In step 0, we set up the Remote XY application and established a wireless communication between the remote and the drone through the help of ESP. In step 1,
MPU 6050 module includes a 3-axis gyroscope and a microprocessor for managing serial communication and data storage. By measuring acceleration due to gravity along the 3-axis, we determine the tilt of the drone.
in step 2, we verified whether the ESCs were working properly and that the motors were rotating in the intended direction, along with the working of the application and the gyroscope. In step 3, we uploaded the final flight controller code into the drone, and when the joystick is moved to the bottom left and back to the center, our drone is armed and is ready to take commands. To disarm the drone, move the left joystick to the bottom right.